All right. Hello, everyone. Thank you so much for attending our session. Today, we'll introduce the security landscape in this emerging Open RAN system for mobile infrastructure and give some of the thoughts and insights we have when testing these ORAN systems. My name is Tian Chang. I'm a PhD student from Penn State University with a research broadly focused on security analysis and testing for mobile systems like 5G and Open RAN. I like hiking or just gaming, and mostly I just like chilling. This is a cool picture of beach. And
hello, everyone. I'm Kai, and I'm also a PhD student from the same lab as Tian Cheng. I do many security researches related to mobile network and devices. And I also like driving to explore many different places.
Right. So whenever we think of mobile security, the first thing that always comes to mind is the phone, right? If the chips on your phone is secure, are the applications maybe they have any backdoor? Well, in fact, just this morning, we were giving another talk on testing the mobile baseband, so you guys should definitely check that out if you didn't have the chance to attend. But what a lot of people don't fully grasp is that we also have an entire architecture of the network supporting this wireless communication, like the cell tower we have shown here. A more formal name for this cell tower network is the radio access network, or RAN, and that is going to be the focus of our talk today. But before 5G, this infrastructure had largely been very much closed and vendor-specific hardware, like this really complex mess you have seen here. But nowadays, with the widespread adoption of 5G and the introduction of Open RAN, mobile network infrastructure is promised to becoming more open, virtualized, and modular. So instead of this huge chunk of specialized hardware, you can use small boxes for radio and then deploy a lot of the functions on general purpose servers, as you can see on the right-hand side. So today, we are mainly here to look at the implications behind this kind of movement.
First, I want to give some analogy of ORAN. When the computers are first introduced, programmers have to work directly with the hardware to write the programs. The adoption of operating systems allows programmers to forget about the hardware. They program on top of the operating system, which is handling the hardware and low-level tasks. This leads to the boom in computers and resulting in our modern modularized hardware managed by the operating system. The internet goes through a similar shift. Before, you will have specialized servers, switches as the backbone of the internet, running proprietary routing and managing of traffic. Fast forward to around 2010, the introduction of software-defined networking brought the idea of separating control from data, using general-purpose hardware and programmable switches. Nowadays, ORAN is like the counterparts of software-defined network, but in cellular network space. For 4G and before, you have vendor-specific, hardware-centric cell equipment. What essentially ORAN promises is to run these previously closed cellular cells as virtualized functions on commodity servers. This opens up a lot of optimization tasks for the mobile network space.
So let's first look at how ORAN fits into the mobile network architecture. We first just have your user equipment, or UE, which are just your smartphones that are served by the network. In traditional 4G and before networks, the cells are provided as a single monolithic proprietary hardware by specific vendors. This means that operators have to rely on the vendors to ensure the functionality and the optimization of this RAN hardware. And they really don't have much of a flexibility to perform their own optimization or customization on these RAN hardwares. And becoming more aware of these problems, in 5G, the architecture is designed to be more software-centric and virtualized. So this includes, first of all, the disaggregating the monolithic RAN into different components, the radio unit RU, distributed unit DU, and central unit CU. With the disaggregation, the protocol stack is also divided across the nodes. It ensures basically from the previous single cell component, which integrates both physical layer operations as well as the software optimization and control tasks to different RAN nodes. So now DU and CU will handle mainly the high-level plan and control tasks, and can be deployed on the cloud or on general-purpose servers. Open RAN is introduced to this landscape to provide even more openness and a smart, intelligent control to these hardware components. ORAN basically introduces a software RAN intelligent controller, or RIC, to standardize and implement these optimization tasks. The RIC interfaces with these RAN nodes through standardized interfaces, And it contains the RApp, which handles latency-insensitive tasks, such as some policy configuration management of run nodes, or just general like the lifetime training managing of AI and ML models. Whereas xApps, they handle more real-time functions, including the direct control and optimization of scheduling, load balancing, and direct handovers. So because of this more virtualization and standardization, ORAN essentially promises network operators to plug and play different hardware components, maybe using different DU, CU, and RU from different vendors to avoid vendor lock-in in previous generations and allow operators to choose the best components for their run.
For a detailed look at RIC architecture, the E2 interface connects the RAN nodes with the RIC. Messages and protocols on E2 interface are standardized by ORAN. The main function enabler of RIC are the xApps, which may perform different optimization tasks. Network operators can choose to use xApps from the third-party providers to get the most optimized network. Other components in RIC support the operation of xApps, and they are running as separate programs in ORAN's service-based architecture. This internal communication and division of internal components are not standardized. I have seen implementations chose to use gRPC or some customized internal messaging systems to deliver the messages. Each RAN node sends standardized reporting messages containing metrics of its operation through the E2 interface. These messages first reach the endpoint of E2 and main message handler in RIC, the E2T. Then the messages will be decoded and routed to each component or xApps. The xApps can then choose to send control messages back to the RAN nodes to optimize the network. Now I want to circle back to this analogy we presented at the start. What ORAN is to the RAN is essentially what SDN has been for the internet for the last 15 years.
Okay, so are ORAN already being used by network operators?
Some aspects, like virtualization and software-centric, definitely. But major operators is still trying to use hardware from a single vendor at the moment because they want to make sure they have someone to blame if the RAN is acting up. But smaller operators or private 5G deployments, I believe, is benefiting first from ORAN that allow you to control and change both hardware and software easily.
And are ORAN already really going to be eventually adopted?
Well, it's hard to say if the entire promises of ORAN are going to be adapted. But one thing for sure is as the use of AI, machine learning, and large language model is consistently a hot topic for the operators. And all these functionalities depend on the virtualization and cloud native of RAN. So this movement to more open and software-centric RAN is for sure happening.
Right, so now we have to talk about some less happy news, because from the previous generations of closed RAN, the internals are largely just unexposed to users. So the closeness basically is guaranteeing the security of these components. But with this sudden shift to openness in this Open RAN, since it is a really critical infrastructure for national security, as an emergency service distribution, and just as message distribution systems, basically any vulnerability can lead to disastrous outcomes. So today we are looking at some of the implications behind this movement. Maybe first, like the user of the network can send arbitrary input to the networks through using software-defined radio with a valid SIM card from the operator. This means an attacker can send any malformed or unexpected payload with malicious intent over the air interface to the radio unit. And since the RU typically just forwards received message without any deep inspection, the malicious payload may eventually reach and processed by the DU and CU. So if there's a bug in the CU, for example, this can lead to crashes and then or unexpected behavior. So as a result, the entire cell may become unavailable or causing a denial of service, so all users connected to the base station are affected. We also have seen this kind of attack caused by malicious user devices in existing networks. Studies have shown that 5G infrastructures can be vulnerable when being sent unexpected inputs. A much more simpler attack would just be using some kind of jammer or signal storm to block the communication, which is very hard to prevent or mitigate. The second threat comes from the supply chains, because telecom operators depend on a vast ecosystem of vendors, manufacturers, and developers that rely on closed source and open source libraries to deliver their RAN software. So any of these libraries could contain unintentional or intentionally malicious code, some hidden vulnerabilities, or just straight out backdoors. The supply chain is a huge concern for the software systems, and a recent study has specifically highlighted this issue given the sudden openness and the disaggregation in 5G and Open RAN. ORAN also promises the use of hardware from different vendors, and each vendor basically have different security practices or supply chain vulnerabilities. That means ORAN typically had to employ a zero trust model to ensure that no vulnerability or attacks can propagate through just one single compromised component and impacts other components. Otherwise, for example, if a malformed input from a deal can crash or some vulnerable component or the xApp, the component is just unable to handle requests from any other RAN nodes. Or more severely, you can even crash the entire E2T. And when this message router E2T crashes, no xApp can deliver or receive any messages from the RAN nodes. Basically, this means that even you have the perfectly functioning xApps in the rig, because this interface is disrupted, the xApps become useless from the RAN's perspective, rendering the entire rig non-operational. So this requires really careful implementation, so malformed or unexpected inputs can never cause system-level outages. And in fact, ORAN itself considers the same threat model in a study on rig security, and they conclude that the rig should not assume that the data received is valid or trusted, and some validation should be enforced to ensure its robustness. And in ORAN's official security studies, they also have a lot more insights that kind of align with what we have discussed or what we'll discuss, but we don't have time to go over all of them today, so definitely check those out. But finally, instead of the previous generation's closed hardware or ORAN RAN nodes, the applications and rigs are deployed in cloud service. And we have seen many reports of potential VM vulnerabilities like container escape. If an attacker takes control of some ORAN nodes or controllers of a different VM in the same server as the ORAN component, then the VM vulnerability could let an attacker to just escape into the overall hypervisor and potentially cripple through the entire control plane of ORAN. But I mean, this vulnerability really is not unique to ORAN, and today, for the later half, we're mainly focusing on the threats caused by malicious users and heterogeneous RAN nodes, and inspect whether RAN and rig can stay robust under this stress.
In this work, we primarily tested 3 implementations. We tested 2 rig implementations. One is the ORAN software community implementation, which can be considered as the official reference implementation. The other one is SD-RAN, which is another ORAN compliant rig. We have also tested open-air interface disaggregated ORAN RAN nodes. These 3 are pretty much the most mature and widely adopted open source components. Among these, we have found 19 flaws in rig and 7 flaws in OAI's RAN implementation. In total, we got 22 CVEs assigned to check these issues. Here's a more detailed breakdown of the types of errors we found. Bugs marked in black are found in OAI's CU or DU component. Brown are found in rigs platforming or dependency libraries. And blue ones are in the xApps. Among the vulnerability types, assertion failure, memory issue, and runtime panic vulnerabilities all lead to component crashes. And both logical errors discovered in xApps leads to the communication channel being blocked. And the impacted RANs will never receive any message from the xApp without any explicit error message, leading to a still C denial of service. These dependency issues are from either customized or third-party message encoder or decoders, and they affect all components using these libraries. Because of the complexity of such encoding-decoding functions, even with extensive testing, they can still contain bugs. This showcases the dilemma operators and vendors often face when dealing with the dependencies. If they use customized in-house built decoders, they may be under-tested. If they use third-party provided ones, then they may not be fully trusted. Finally, the rig implementations can face both memory issues and runtime panic. This is because they use a combination of memory-safe and unsafe languages. The memory violations could potentially lead to remote code execution if memory protection like ASLR or stack canaries are not properly implemented. Even in memory-safe languages, we found some Go programs using C Go calls to invoke APIs in C++, and vulnerabilities in those C code can still make this Go component vulnerable to memory violations. Those are some great findings, but all of them are on open source components. So maybe the commercial ORAN systems are more secure?
Well, I'm glad you asked because we also collaborated with Trend Micro and tested a commercial ORAN rig. We can now really reveal the details of the rig vendors due to the NDA, but it is designed to be a closed source, commercially provided, and employs a zero trust design. But do this make it secure? Well, since we do not really have any source code access and cannot do advanced code analysis, we rely on really straightforward black box API testing. And even then, we still uncovered 4 implementation level vulnerabilities that could cause denial of service and unexpected component behaviors. Those are triggered by some overly long requests or unexpected request formats. For example, when we provide a JSON file when a simple string is expected. And all of our findings just prove that although ORAN's open and virtualized design creates opportunity, its reliance on software-centric design introduces many vulnerabilities as well. So we want to now show you some of the insights of how we found these bugs. We can now cover every technical detail in the talk, so we'll leave a link to our paper at the end. But we'll also focus mainly on the open source implementations because that allows us to do more advanced code analysis. But our approach will be generally adaptable to other commercial implementations as well. We'll mainly focus on our rig testing, but we used a similar method for run testing. Let's maybe first look at the limitations of existing testers like AFLnet, which is a well-known protocol tester. But by design, they can only test one program at a time. So say we want to test the rig, maybe this xApp1, by sending the test inputs directly to the xApp. But that we had to require significant harnessing, like identifying the protocol and message formats used for each component we want to test. And such internal message implementation detail is not really defined by ORAN specifications. So different implementations can choose different protocols with customized message formats. So this kind of harnessing and testing really is not scalable and has to be manually conducted for each tested component for each implementations.
Yeah, to solve this challenge, we take an end-to-end approach, where we test the entire rig as a whole by sending our test inputs only through the E2 interface. We still do fuzzing, but since E2 messages are standardized and well-defined, this allows us to automate the test generation process and make it scale to different implementations. In addition, this also ensures that all found bugs are exploitable by a misbehaving RAN. The right-hand side simplifies the problem we are targeting. Given a targeting rig, which could be an xApp or a platform component like the E2T or subscription management, our goal is to send the test inputs through the public E2 interface and then ensure our test inputs can eventually reach our target and find the bugs. In this end-to-end testing approach, several challenges has to be addressed. First, we need to generate the test inputs under the right constraint. Say we want to test the xApp, the test message has to get past E2T's check and route it to the target. Here's an example of E2T checking the target message's target component ID. And if the ID is not valid, E2T simply discards the test message, and this test message cannot reach the xApp. All intermediate components enforce specific checks on fields like message type or specific field values. So we need to make sure we constrain the test inputs to satisfy these checks. If the input generation is under constraint, the malformed test inputs may be discarded early by the E2T, not even reaching the xApp. On the other hand, consider the xApp contains 3 execution paths, but only one can lead to the vulnerability. If the input is over-constrained, these paths leading to the vulnerability may never be explored by the generated test inputs because they are not diverse enough to discover this path. To address this, we take a layered testing approach, where we first test the component directly connected with the E2 interface, which is always the E2T, and gradually move to deeper components. When testing each component, we collect the appropriate constraints so the test inputs can reach the next component. However, this approach requires the understanding of layered dependencies of components. To solve this, we use dynamic tracing during runtime of ORAN to find this information. This shows what we have discussed so far. We instrument the source code and deploy it with benign RANs to collect normal operation traces. From these traces, we infer the component dependencies in rig and how different messages flow through each component. What is the entry-exit point in each component for each message? The messages are also used as initial corpus for our fuzzing.
And after we found the component dependencies, we ran some static analysis between the message entry and exit to find all execution paths in the component, which we use as just branch conditions as constraints for generating the targeted test inputs. But applying static analysis is also challenging. Here it shows for a single component in ST-RAN's rig implementation, it can contain about 500,000 lines of code. And of course, this includes a lot of generated API codes and test files, but still analyzing this much of code is just not achievable by some simple static analysis, especially since our goal is to follow the control flow and find critical path conditions. And if we count the number of functions, there are more than 6,000 functions, and that is excluding all of the test and API files, just the processing logic of the component. This is just too much for static analysis to handle, and we will encounter a path explosion problem, very quickly run out of resources like memory and could not produce any useful results. So we had to carefully decide which parts of the code to analyze. We start with some pretty standard techniques. For example, we use a PDG, a program dependency graph, to focus only on critical branches that determine whether the message is accepted or discarded, ignoring other less relevant execution paths. And we apply the backward data flow analysis to extract the constraints from these branches. But we later realized this still isn't enough because ORA messages contain many fields with verifying processing logic, which means that we also have to be selective about which functions we analyze. So maybe take these two functions as examples. Just from their names, you can probably guess which we want to analyze and which we don't. The first is doing some kind of validates input to a component, where the second just retrieves the information from a URL. So we obviously care more about the exact checks performed on the input to extract those constraints, but we don't really care about the internal logic of a data retrieval function. But how can we even distinguish between such functions in practice? Do we just filter them by their names? But for a simple component, there can be thousands of functions. Here's just a really small list of them, and manually labeling them definitely is not feasible, not to mention all of the functions from dependent packages. Or do we ask an LLM to reason through them for us? But that's also slow and expensive. Or maybe we can find some structured control flow pattern that differentiates between them. So when looking at the code, we actually noticed something. Here are the two functions we use as examples. Do you notice any difference between the first more meaningful function we want to analyze versus the second generic function? Well, if you look closely, you can see the difference in how they're being used. The first function is invoked in a very narrow context by just one package and at only two sites, if we exclude the unit test. The second function, by contrast, is invoked from multiple locations across multiple packages. And this led to our core insights, which are functions with narrow usage patterns are more likely to be specific validation functions, while functions with broader usage tend to be more generic helpers or utilities. We also use some more fine-grained heuristics, like how we analyze the intercomponent code analysis, but the high-level idea is just this simple, and it actually works really well in practice. So that is the key of our message generation. We use a scalable static analysis to generate path constraints that produces targeted fast inputs for each component.
Now we can see the entire workflow of our system. Due to time constraints, you can see I'm still leaving out some details, like how exactly our fuzzer works, or our grammar-aware message generation. We will leave a link to our paper at the end. Please check it out if you are interested. As we introduced, in the dependency analysis phase, we use dynamic tracing to find the dependency between components. Then we apply static analysis to find the input constraint we need to enforce, so the test input can reach the component under test, which is the CUT, marked in red. The input constraint is used for message mutator, which generates test messages based on the ASM1 E2 message definitions available in the technical documents. The generated test inputs are sent through the E2 interface to the rig to test the target with a runtime monitor responsible for collecting code coverage feedback and report any crashes caused by the test input. We will present some demos of our findings. The first is the vulnerability in the disaggregated RAN. A malicious user sends an input to the RAN, causes the CU to crash, and lead to the loss of service of all connected users. This is our attack setup. We have a benign RAN, two benign user devices, and an attacker-controlled malicious user equipment, which is a software-defined radio. We have 3 terminals on the left, which are DU, CU, and core network. We will start all of them to form a benign RAN, which can provide the service to the users. And we also have the attacker terminal on the right-hand side. And then we connect both of the phones to the RAN. And as you can see, the 5G sign is already there, which means the phone is ready to go. Now, as you can see, both of the phones can browse in the network smoothly. Then we can start the attacker-controlled malicious user equipment. And we can also send a malicious message to the RAN. It's clear that after processing the malicious input, the CU crashes immediately. As a result, both of the phones lose their network service. However, as the DU and RU are still running, the phone may still believe it can get a network service, and it is still showing the connectivity.
All right, thank you, Kai. So our second demo shows a malicious run node sends an unexpected message to the rig, causing the E2T to crash. And then because this message router is down, all connected run nodes can no longer deliver or receive any messages from the rig. Here you can see 3 terminals, one for the rig, one for benign run, and the last one for an attacking run. Rig components are deployed in Kubernetes, and they are running here as expected. So let's focus on the E2T this time and take a look at the E2T's log. You can see that it is running normally as well. And let's first connect the benign run to the rig. Here, the connection is being set up, and it actually receives the setup success response messages. And if you fast forward a little bit, you can see the benign run starts sending metrics and receiving controls. The message ID just keeps changing, and the metrics are being sent continuously to the xApp. But now consider if an attacker gains control of another run node connected to the same rig. This might be from the backdoor or some cloud vulnerabilities like we had discussed previously, right? And then it can send the malicious message to the same rig. On the left-hand terminal, you can see the E2T just immediately crashes due to the message causing a segmentation fault. And if you look closely at the Kubernetes status, you can see the crash history of the E2T. And since E2T crashes, the benign run no longer sends or receives any messages. You might think the Kubernetes will just restart the E2T pod and it'll be fine in a couple minutes. But depending on the implementation, even after E2T restarts, the benign run may have to manually reestablish this connection to resume the normal operation. And this is actually the case in this example. The benign run has to restart as well to resume the connection. All right, so some final points we want to emphasize. 5G and Open RAN's aggressive shift to openness means a great number of attack surfaces is opening up, and we believe not nearly enough people are talking about these huge security concerns, considering the attacks this could cause for such a nation-critical infrastructure. And there's a lot of open information on ORAN. The specs are easily accessible. And just 2 weeks back, the ORAN software community releases the latest release version of the rig. You can easily deploy them in Kubernetes, and all of the codes are open source. You can just start by reading the code and maybe bug hunting to contribute to the security of ORAN. And finally, in this talk, we mainly talk about the crashing bugs. There can be also way more attacks that is more stealthy, but also harder to find. For example, side channel to profile run vendors or rig algorithms, privacy leaks given the amount of data ORAN handles. Those are all very interesting topics that we have not had the time to really look deep into. And we finally want to thank you all for listening to our talk. You can find our contact info here. You have the QR code to our paper and the code. Feel free to drop by the rep area for any questions. We want to thank all of the collaborators who couldn't present here with us, and our advisors for their feedback, and our Black Hat coach for their inputs. We also thank the developers of the open source systems we had tested. They're all very collaborative and active in addressing the issues. And finally, we want to thank Trim Micro for working with us for testing the commercial Oren rig. Yeah, thanks so much.
Thank you.